Rosen, Discrete Mathematics and its Application, Section 4.2, Integer Representations and Algorithms. Today we will study binary modular exponentiation, and there's a related algorithm that you can use to accomplish this. First, let's just talk a little bit about why this is important. In cryptography, we will often need to find results of the form b to the n mod m, where those are all often large integers. And if we use a binary expansion of the exponent, then we will be able to more easily calculate b to the n and also b to the n mod m. So if I use a binary expansion of n, I see that I can break n into the sum of powers of 2, and you only include those powers of 2 for which the bit would be a 1. And since this circled portion is a sum, I can break the exponent, that is an exponent, into a product of b raised to each of the powers of 2 for which the a is a 1. And then, in order to compute b to the n, we only need b squared, b squared, b to the 4th, b to the 8th, as needed to calculate the binary power. Okay, so let's do an example. I want to calculate 3 to the 11 using this method. And if I broke 11 into its binary expansion, I'll have 1 times 2 to the 3rd, 1 times 2 to the 1st, and 2 to the 2 squared, and 1 times 2 to the 0 power. No, not 2 squared. All right, so that's 2 squared is in the 0 section. So I've got 2 to the 3rd, 2 to the 1st, and 2 to the 0 power as my exponents here. Okay, and then note also that I can take 3 to the 8 and make it into 3 squared, squared, squared. So I can actually get 3 to the 8 by knowing 3 squared. I can get 3 squared by knowing 3 to the 1st by squaring it. And by that iterative approach, I can see that 3 to the 8th is 81 squared, which is 65, 61. 3 squared, of course, is 9. And 3 to the 1st is 3, to give me 177,147 as my result, 3 to the 11th. And let's break that. Let's use this as an example to look at b to the n mod m. Let's say we wanted to get 3 to the 11 mod 4, and the whole thing is mod 4. Well, we can break that down. 3 to the 8th times 3 squared times 3 to the 1st mod 4. And we saw earlier that we can take the modulus with respect to 4 of anything inside of this, any factor, any term. So this is going to be equal to 3 to the 8th mod 4 times 3 squared mod 4 times 3 to the 1st mod 4, all mod 4. And 3 to the 8th mod 4, that's 65, 61 divided by 4 remainder is going to be a 1. And 9 divided by 4 remainder is 1. And 3 divided by 4 remainder is 3, to give mod 4 to give me 3. And the beauty of this approach is that we never had to calculate a number as large as 177,000. We only had to deal with smaller numbers to using this modulus of internal factors. Okay, so let's take this to a larger example. All right, we want to find 3 to the 644 mod 645. And we'll use the binary expansion of 644 to show that 3 to the 644 is equal to 3 to the 512 times 3 to the 128 times 3 to the 4th mod 645. And as we said, we can take the modulus of any factor, any term inside the argument of a modulus, and the result stays the same. So I've got 3 to the 512 mod 645, 3 to the 128 mod 645, and 3 to the 4 mod 645. And oh, by the way, well, first of all, we got to calculate each of these, and it's not necessarily straightforward how to do it, but it will become clear in just a moment. But also note that we have another product in here. 3 to the 128 mod 645 times 3 to the 4 mod 645, we can take the modulus of that to keep these numbers small, and that way we're only multiplying two numbers that are less than 645 each time. This star here represents a substitution we'll make in just a moment. Now let's go figure out how to calculate all the binary modular powers of 3. Well, we're just going to use an iterative approach where we substitute earlier powers of 2 as the exponent to get the next power of 2 exponent of 3. All right, so 3 to the 1 mod 645 is 3. 3 squared mod 645 is 9. 3 to the 4th mod 645, well, that's 3 squared mod 645. But I can take the modulus of any factor, any term in the argument of a modulus. So that's going to be 3 squared mod 645 squared, still mod 645. But I have an expression for that, and that's at 9. I can plug it in, get 9 squared mod 645, which is 81. All right, well, how about 3 to the 8th? Well, 3 to the 8th is 3 to the 4th squared mod 645. I can take the modulus of that factor, and I get 3 to the 4th mod 645 squared, but we've already calculated that value in 81, so we can just substitute 81 in for 3 to the 4th mod 645, square it, and we take the modulus of back to 645 and get 111. All right, how about 3 to the 16th? That's going to be 3 to the 8th squared mod 645. I can take the modulus of that and then square it and maintain the same value, but I've already calculated 3 to the 8th mod 645. It's 111. So I substitute that in, square it, take the mod of 645, and get 66. And that way we build up all the powers of 2 that we need, and so on until you get 3 to the 128 mod 645 is 396, and 3 to the 512 mod 645 is 111. And notice that often this table of values will repeat as you get higher and higher. Okay, so we don't need to go higher than 512 because that is our largest exponent in the 3 to the 644 representation. Now I can substitute in all of these values here to get 3 to the 644 mod 645 is 36. And that is an example of binary modular exponentiation.